Hi, welcome back. In this video, we're going to introduce isomorphisms and do a few examples. So let's start with some definitions. So let's say we have a linear transformation T from V to W. Then we're going to define what it means for T to be one-to-one, the definition of an onto linear transformation, and then finally we'll define an isomorphism. So the linear transformation T is said to be one-to-one if for all u and v in the domain, T of u equals T of v implies that u and v are the same vector. So it basically means that anything that gets hit in W only gets hit by one thing. It can't get hit by more than one thing. The pre-image of anything in the range, the pre-image just contains one vector. And T is onto means that the range of T is all of W. It's the whole codomain. Everything in W gets hit at least once by something in V. And then we say that T is an isomorphism if it's both one-to-one and onto. Let's look at a couple of pictures to visualize some of these things. So here's the vector space V. Let's say we've got a couple of vectors, V1, V2, V3. And then there's the codomain W. It's got a few vectors. And the linear transformation T sends V1 to W2, V2 to W3, and V3 to W4. And we see that W1 didn't get hit by anybody. So the range of T is not the entire codomain. But everything that did get hit got hit once. So T is one-to-one in this picture, but T is not onto. And another similar picture, let's say here's V. It's got these four things in it. And W has just three things in it. And here's T. It sends V1 to W1, V2 to W2, V3 to W3, and V4 also goes to W3. So we can see that everything got hit. The range is the entire codomain W, but W3, that vector, got hit twice. So it didn't get hit by just one thing. So this thing is onto, but it's not one-to-one. All right, let's look at an example. So here we have a linear transformation that goes from the vector space of all 2x3 matrices to the vector space of all 3x2 matrices, and it's given by T of A is just equal to the transpose of A. So it just says take the transpose, and that's our linear transformation. So the question is this an isomorphism? We can check to see if it's one-to-one by assuming you've got two matrices that go to the same thing. So T of A is equal to T of B. So if we can prove that A must be equal to B, then we've proven that T is a one-to-one linear transformation. Well, T of A is just the transpose of A, and T of B is the transpose of B. So using the properties of transposes, I can take the transpose of each side, and those have to be equal. Well, A transpose transpose is just A, and the transpose of B transpose is B. So we've proven that A has to be equal to B, so it's a one-to-one linear transformation. All right, let's check onto. So onto means that if we just grab an arbitrary matrix in the codomain M32, then it has to get hit by something. That means it's onto. If we just grab any arbitrary vector in the codomain and show what it got hit by, then we're done. We've shown it's onto. So let's grab a matrix in M32, and then if we take the transpose, that's in M23, right? So the transpose of B is in the domain of our linear transformation. So let's do T to that thing. T of B transpose is the transpose of B transpose. Well, using properties of transposes, we know that's B. So we found something that got sent to B. We grabbed an arbitrary vector in the codomain, and we found a vector in the domain that got sent to it. So we've just shown that that is in the range, and it's an arbitrary vector, so that means that T is onto. So yes, T is an isomorphism. All right, so let's look at a theorem. Theorem 6.6 says that T, the linear transformation T, is 1-to-1 if and only if the kernel of T is the trivial subspace of the domain. So the kernel of T just has one thing in it, the zero vector. This gives us a nice, easy way to check if a linear transformation is 1-to-1. Let's prove this because this is an if and only if statement, so it's a biconditional, and I want to illustrate. You have to do two things. We have to prove both directions. So let's start by supposing that T is 1-to-1. And now we're going to show that the kernel has to be just the trivial subspace. It just contains a zero vector. Let's take a vector in the kernel. V is in the kernel of the T. T of that vector, that has to be the zero vector in W. But we also know that the zero vector from V got sent to the zero vector in W. That's one of the properties of linear transformations. But we know T is 1-to-1, so those two vectors have to be the same. So we just grabbed an arbitrary vector in the kernel, and we showed that it had to be the zero vector, so that means that the kernel of T just contains the zero vector. And I'm using subscript V just to emphasize zero vector in the kernel of T, that is the zero vector in the domain. But the zero vector in the codomain, that's the zero vector in W. All right. So now let's suppose the kernel is just the zero vector. So suppose that the kernel of T just contains the zero vector. And now we want to show that that means T is 1-to-1. Let's suppose we've got two vectors in V that get sent to the same thing. Remember, the definition of 1-to-1 is that if two vectors get sent to the same thing, then they're really just the same vector. So now our job is to show V1 is really equal to V2. Well, T of V1 minus T of V2 has to be the zero vector in W, right? Because T of V1 is equal to T of V2, so when we subtract, we get the zero vector. But because of the properties of linear transformations, that means that T of V1 minus V2 is the zero vector. Well, this means that V1 minus V2 is in the kernel of T. And we assumed that the kernel just contained the zero vector. So V1 minus V2 is the zero vector in V. But that just means V1 is the same as V2. So we've just proven that T is 1-to-1. All right, let's do another example. So suppose the linear transformation T goes from P5 to P4, and it's defined as differentiation. So T of the polynomial P is just the derivative of P. Is this an isomorphism? Well, let's check the kernel. Let's try to use the theorem we just proved. T of this fifth degree polynomial is equal to the zero polynomial in P4 if this derivative, so this is the derivative of that polynomial, is equal to the zero polynomial. So I just differentiated that fifth degree polynomial and I got this fourth degree polynomial, and that's got to be equal to zero because it's in the kernel. The polynomial was in the kernel. But this just means that all of those coefficients, A1, A2, A3, A4, and A5, have to be 0. So that means the only thing in the kernel are just constant polynomials. So the kernel of t is the span of the real number A0. So it's just all the constant polynomials. Well, that's a little more than the 0 polynomial. So t is not 1-to-1 because the kernel of t is not just the 0 polynomial. So this is not an isomorphism because it's not 1-to-1. We don't have to check and see if it's onto. All right, so let's look at a few more definitions. So we've got a linear transformation from V to W. We define the nullity of t to be the dimension of the kernel of t. And we define the rank of t to be the dimension of the range of t. So t does not have to be defined by a matrix, by matrix multiplication. These are similar dimensions of similar subspaces when we talk about matrices, but t could be a linear transformation from any vector space to any other vector space. These do not have to be linear transformations defined by matrices. So we have another theorem, 6.7, which gives us a way to check for onto. So it says that the linear transformation t from V to W is onto if and only if the rank of t is equal to the dimension of W. Remember, the rank of t is the dimension of the range of t, and the range of t is a subspace of W. So if the dimension of that subspace is equal to the dimension of the entire vector space, well, that means that that subspace is that vector space. It's the whole thing. So that means that t is onto. Let's do an example. So here we have a linear transformation from P2 to P3. And it's given by t of the second degree polynomial a0 plus a1x plus a2x squared is equal to this third degree polynomial a0 plus a1x plus a1 plus a2x squared plus a0 times x to the third. Is this an isomorphism? So we're going to try to use the theorem. We're going to check to see if it's onto by checking the dimension of the range. So this polynomial is in the range, right? This is just sort of a typical third degree polynomial that's sitting in the range. So I can rewrite this polynomial as a0 times 1 plus x to the third plus a1 times x plus x squared plus a2 times x squared. And that means we've got a basis for the range because these three polynomials are actually linearly independent. So basis for the range is the polynomial 1 plus x to the third, polynomial x plus x squared, and then the polynomial x squared. Those are linearly independent, and it's pretty easy to show that. That's a basis for the range, so that means that the rank of t is 3. The dimension of the range is 3. But the dimension of P3 is 4. So by theorem 6.7, that linear transformation is not onto. So this cannot be an isomorphism. All right. We've defined 1-to-1, we've defined onto, and we've defined isomorphisms. And we've defined the nullity of a transformation and the rank of a transformation. And we've done a few examples. So you'll see more of these in the next couple of sections. And I'll see you in another video.